Assalamu alaikum everyone. This is my new pulse width modulation code that I did. This is a pure bare metal code. And here is this circuit. So here is this 4 LEDs for 4 different pulse width modulation signals. You can assume them as 4 different motors, like drone motors. If we power it, so here is this one is not blinking. There is this problem I couldn't fix. I tried with different timers with different channels, but I couldn't fix it. The reason you are seeing them dimming and glowing is because this effect that I created here in the code. So let me just explain to you the code a little bit. So first of all, we are doing pulse width modulation. What pulse width modulation basically is that we are modulating the width, the duty cycle. We want to keep it open for a certain amount of time, and we want to keep closed for a certain amount of time. I'm going to explain it to you here. First of all, I'm not going to go into details how these things are. This is just a 2 enabler register that I use. We are using timer 2, and for timer 2 in the reference manual, the timer 2 is here under advanced peripheral bus 1, and we are going to use general purpose input output pin A, advanced peripheral bus 2. These two are in 2 different peripheral bus, so we need to enable both of them. For this reason, we have to turn on both of the advanced peripheral bus. Here is this reset. GPIO A is under control register low, so we have to configure that. So in order to use the pin 0, 1, 2, 3, we have to first reset them, and then we're going to configure pin 0, 1, 2 and pin 3. Each pin takes 4 bits, so 0, 4, 8, 12. 0xb means 1011. Here we need to configure the control register low. For every 4 bits there is one pin. For pin 0, pin 1, pin 2 and pin 3, we have to modify these 4 pins. What we need: alternate function output push pull. Alternate function is to make the pulse width modulation so that it makes the alternating signal pulse. Then we want the max output, so we were taking 1 1. First it is on the right, it is mode, then on the left it is configure. We have to keep the configure on the left, the mode on the right. So we are going to take 1 0 and 1 1. So 1011 in hexa means 0xp means 1011. We are configuring pin 0, 1, 2 and pin 3. So we basically set them to alternate function output push pull and the max speed. So next come to the main thing, the pulse width modulations. First of all, there is the prescaler. Prescaler is the register that scales down, if I'm not mistaken, it is the register. It scales down the original clock speed of the microcontroller. Since I'm using Blockville, this Blockville microcontroller is at 72 megahertz. What we're essentially doing is we're scaling it down to 1 megahertz. We are dividing it by 72 to get the output of 1 million hertz. So we need to keep the number here 7 to 1 because the hardware adds a 1 with the result we will be getting is 1 megahertz. So we scaled it down for the timer. Then there is this auto reload register, the register that places the value to 0. For an usual drone we want a speed of 400 hertz, 400 times a second. The output that we want through this pulse width modulation is 400 hertz. So what we essentially need to do is get the 400 hertz output. How we are going to get it? We're going to divide 1 million by 400 hertz. In 400 we're going to get 2500. So we have to keep the value of the auto reload register to 2500. This means that after 2500 counting, the auto reload register will reset to 0. It will again start counting from 0, and since the hardware adds a 1, so we're gonna give the value to 499. After every 2500 count, the auto reload register will reset it down, and it will keep doing 400 times in every second, so the result would be 400 hertz. Here is this capture compare mode register 1. We are configuring these 2 registers. They are in the reference manual. We're going to capture compare mode register. So what we want here is the output compare OC1. OC1, here we want it to be pulse width modulation mode 1. So it is 110. To configure it, we want it to be 110. This is for channel 1, and this is for channel 2. This is the capture compare mode register 1. This mode register 1 has 2 channels, and the mode register 2 has also 2 channels. We want to configure those channels to pulse width modulation 1. So to make the output compare to pulse width modulation 1, we want to set the bit 4, 5 and 6, and for the channel 2, 12, 13 and 14 to 110. We are doing from the bit 4, and for the bit 12 to 0x7. First of all, we also want the capture compare mode register 1 to reset. So we want 4th position and the 12th position bits to set them to 111 and reset them. Then we want to set them to 110. 0x6 is the x value. So here we set the capture compare mode register 1, reset it and then configure it. Similarly, we reset it, the capture compare mode register 2 and configure it. Since we have already configured these channels, channel 1, 2 and then channel 3 and 4, so we want to enable them, give them the power, the clock signal. So we are enabling it to 0, 4 and 8 and 12 bits. Here 1E is the enabler register. Capture compare 1E. 0 means not active and 1 means active. We want to keep the capture compare enable register for every channel. This is for the channel 1, this is channel 2, this is channel 3 and this is channel 4. So capture compare mode register being enabled. So there is this timers. So this is the auto reload register, this is the prescaler, and this is the counter. So the signal comes, it scales down to a manageable signal. The counter starts counting. When it reaches the auto reload register, the value, then it will reset. Here the signal is getting scaled down, and there is this output control, and there is this channel 1 and channel 2, channel 3 and channel 4. We are getting the output in 4 channels. Okay, and this is the capture compare mode register 1 controls this 2 channel. Capture compare mode register 2 controls this 2 channel. There is difference between the capture compare mode register and capture compare register. Capture compare mode register is controlling the channels, and capture compare registers is setting the value of the duty cycle. Here is the signal. So this is the period. Okay, the signal starts here and ends here. This is called the duty cycle. This is called the off cycle. We are controlling the duty cycle of a signal, and sometimes we want to keep it 25%. Sometimes we want to give it 50%, sometimes we want to give it 75%, sometimes we want to give it full duty cycle. The more is the duty cycle, the higher power we're going to get. What we're doing it here, first of all, we are resetting it to 0, so it does not start spinning at random speed from the beginning. So we want to make it 0 at the beginning. Then we come back to the control register. When we will turn it on, the timer will start counting. If you keep it 0, the counter will not count. We have already done everything. Now we want to give it a certain amount of value. Let me explain with this one. If we keep the capture control register 0 value, this means the duty cycle is 0. If we give the capture compare register 625 value, that means we are giving it 25%. Since 100% is 2500 count, so from 0 to 2500 count is the full cycle. Since the hardware adds a 1, this means we're giving the full duty cycle. The motor will be getting power full cycle, and it will spin at a dangerously high speed because it is staying on for the full cycle. 1249, that means we are turning it on for 50% of the time. It's spinning at a medium speed. What we did here is we tried to make a simulation of breathing, and the video that I showed initially of the LEDs are basically the simulations. So these are the two variables. We set an initial speed 0 and given steps 5. We are running this infinite loop. First of all, we are increasing 5 steps in every loop cycle. Here is the logic is that whenever the code will reach the maximum loop cycle, this 2499, we want the steps to be a negative value, so it goes back. Whenever we are increasing from 0 to 2500, we are giving the motor or the LED the higher duty cycle slowly to the full duty cycle. When it reaches to the full duty cycle, we don't want to increase more the speed. speed, because this is the maximum speed we have already reached. So we want it to go back from 2500 to 0. The LED will go from higher brightness to dimming. So when it is reaching the highest peak, steps value is getting negative, and when it's reaching the lowest peak, the steps value is getting positive. So we are going from 0 to 2.99, again from 2.99 to 0, then again from 0 to 2.99. This is how it goes. And we are giving the dynamic speed for every LED. We are giving a dynamic value so that it creates a simulation from dim to higher brightness power to dim. Since I don't have the PLDC motor or ESC at this moment, so I tried to simulate this pulse width modulation with my LEDs. What is the outcome of this is that we are going to get a 400 Hz signal from these 72 megahertz low fill, and we are modifying the duty cycle of the signal. We're controlling from 0 to 1 to 3 to 100% of the duty cycle. Then we are controlling it back to from 100% to near 99 to all the way back to 0. We are completely controlling the whole signal. And here is one more thing: if you just keep it, and it will just change the signal so faster that you cannot see it with your bare eye, because the 2500 counting is so fast is that your bare eye will not catch that. So we want it to wait every 5 steps is goes. We want it to wait after a certain amount of time, so we can visualize after this 5-step progress what is the brightness of the LED. The while loop will start this cycle. Every cycle it will increase the step 5, then it checks if it's in this logic. If it does not fall in this logic, then it skips this. If then it's setting the value for these registers, then it is again going back, increasing and coming and checking it. So it goes and goes round. So it is doing it pretty fast enough for our bare eye not to capture it. So we want to slow it down. We want to loop to waste sometimes in another loop. We gave here a for loop. We don't want to do it for a practical application, but for the simulation we were doing it because we want to visualize it. It is taking another 3000 loop cycle. For every loop cycle here, it has to do 3000 another loop cycle. In every loop cycle it is doing not one loop, actually it is actually doing 1001 loop cycle. So enough of explaining everything. There is a lot more comments than the actual code is for my understanding. So here are 4 different LED. You can think of them as 4 different modes. We are doing this as a simulation. We have controlled this for 2000 loop cycles as I explained in the code. These LEDs are going to dim to all the way to brightness. So let's see this. This is the breadboard power supply. Let me power it back on. As you can see, they are getting higher brightness. This one it is not getting turned on. I don't know the reason. I thought maybe the pin is broken or the other registers or wires have any physical wiring problem. No, I tried with different pins with different timer settings. I rewrite the code, but I couldn't fix it. Thank you for watching it. Bye. Allah Hafiz.